Imagine you're standing in a freezing tent on a roadless gravel bar in the Alaskan wilderness.
Yeah, one of the most remote places you can possibly be.
Exactly. I mean, you are completely cut off from the world. There is no power grid. There's no cell signal for 100 miles in any direction.
Not at all.
You're just huddled over a folding table, staring at this cheap, off-the-shelf consumer laptop that's barely struggling to stay alive on a portable generator.
Right.
And your entire job, sitting in that muddy tent, is to save a multi-million-dollar salmon run from potential biological collapse.
It's incredible. It is arguably one of the most high-stakes, localized conservation environments on the planet right now.
Right.
Because the data gathered in that exact tent, it dictates the survival of entire ecosystems. Not to mention the economic survival of commercial fishing fleets.
Yeah, the pressure is immense.
Yeah.
And today, for our deep dive, we are going to look at why, in that very specific environment, a mathematical error of 23% is exactly what you need to save the ecosystem.
It sounds completely backwards, but it's true.
It does. And conversely, we'll talk about why an artificial intelligence system boasting a perfect 0% error rate would actually trigger a total systemic failure.
Which is fascinating.
Right. We are exploring this single, just wildly elegant engineering idea that completely rethinks how a remote field camp can accurately count thousands of migrating salmon using AI.
And doing it without any heavy computing power.
Exactly. Without heavy computing and without needing a connection to the internet.
It really is a masterclass in realizing that sometimes you don't need a more powerful computer. You just need to fundamentally change the shape of the data itself.
Yes. So we're pulling all of this from a really fascinating research dossier. It details a February 2025 preprint.
Right. The MIT and Caltech paper.
Yeah, the paper is titled Counting Fish with Temporal Representations of Sonar Video, and it's authored by this computer vision for conservation team spanning MIT, Caltech, and UMass Amherst.
That's Van Brunt, Kay, Hawk, Perona, Van Horn, and Beery.
That's the team. And we are also grounding this conversation in the foundational 2022 Caltech Fish Counting dataset, which, from what I understand, really laid the bedrock for this specific branch of computer vision.
Oh, absolutely. That dataset is crucial because it provides the ground truth. You know, it's the raw material that allows us to even ask these questions about efficiency and accuracy in the first place.
So my mission today is to pull this all apart, just strip it down to the studs and figure out how these researchers managed to squash hundreds of hours of heavy video into something a basic laptop can digest in a single glance.
And it really is a single glance.
I'm going to be mapping these concepts onto the real world for you, the listener, and I am relying on you to anchor us in the mechanics.
I can certainly do that.
Like to explain the physics, the mathematics, and just the absolute reality of what this AI is doing beneath the hood.
Happy to. Because to understand the genius of the solution here, we first have to really understand the sheer physical hostility of the environment.
Okay, lay it out for us.
Well, the problem isn't necessarily the fish themselves. The problem is where the fish are and, how they behave.
Let's start right there, actually. Walk me through the actual mechanics of how fisheries agencies have historically tried to get these escapement counts.
Sure.
And just to clarify, when we say escapement, we mean the fish that have successfully evaded the commercial fishing nets downstream, right?
Exactly.
Like they're making their way up the river to spawn.
That is the core metric. I mean, fisheries management is entirely dependent on knowing that exact escapement number.
Makes sense.
And for decades, the primary method for getting that number was, it was incredibly rudimentary. Management agencies would build these physical counting towers on the banks of rivers.
Like actual wooden towers?
Yeah, scaffolding, essentially. A human technician would stand on top of that tower, literally looking down into the water, holding a mechanical clicker in their hand.
Oh, wow.
And they would just visually count the fish as they swam past.
Which sounds completely exhausting. I mean, you're dealing with glare off the water, rain, wind, and just the raw mental fatigue of staring at a moving current for hours on end.
The fatigue is a massive variable. You can't underestimate it. But an even bigger problem is the physical nature of the rivers themselves.
What do you mean?
Well, if you picture a pristine, crystal clear mountain stream from a nature documentary, sure, a counting tower makes perfect sense.
Right, you can see right to the bottom.
Exactly. But rivers like the Kenai or the Nushagak in Alaska, They are heavily glaciated.
Ah.
They're loaded with something called glacial flour.
Glacial flour. Okay, that's the incredibly fine rock dust created when a glacier grinds against the bedrock, right?
Fancy stuff.
And it doesn't settle to the bottom. It just stays suspended in the water column.
It creates what's known as a colloidal suspension. The water basically turns into this opaque, milky, grayish-brown soup.
Oh, gross.
Yeah, the turbidity is so high that light literally cannot penetrate more than a few inches.
So the towers are useless.
Essentially, if a salmon is swimming 2 feet below the surface, a human on a tower cannot see it, period.
Wow.
And add to that the biological reality that salmon do not just migrate during a convenient 9 to 5 window.
Right, they don't clock out.
They migrate heavily at night, actually. So human visual counting and even underwater optical cameras using visible light, they fail completely in these environments.
You simply can't count what the physics of light will not allow you to see.
Exactly.
So how did the industry bypass the visibility problem? Because, I mean, the footage this new 2025 AI is analyzing isn't traditional video, is it?
No, not at all. The breakthrough came when agencies stopped trying to use light and they started using sound.
Sound.
Yeah. Around 2018 to 2021, there was this major widespread adoption of imaging sonar technologies.
Okay, I think I've heard of these.
You'll often hear these systems referred to by their acronyms or brand names, like DIDSON, which stands for Dual Frequency Identification Sonar,
Didson got it.
or the newer era systems.
So they essentially put an acoustic camera in the river.
That's exactly what it is. The unit is submerged right on the riverbank, looking up perpendicular to the current.
Okay.
But instead of capturing photons through a lens, it emits incredibly high-frequency acoustic beams.
Like radar.
More like echolocation. It fans out dozens of overlapping acoustic pulses across the water column many times a second, and it just listens for the echoes.
Okay, so it's creating a high-resolution, moving image out of sound. What exactly is bouncing the sound back? Is it the scales of the fish?
It is primarily the swim bladder, actually.
Oh, really?
Yeah, a fish's swim bladder is filled with gas, right?
Yeah.
And the density difference between that internal pocket of gas and the surrounding water creates a highly reflective acoustic boundary.
Oh, that makes sense. The sound hits the gas and bounces back.
Precisely. When the high-frequency sound wave hits that swim bladder, it bounces back a very strong signal. Solid objects return bright echoes. Empty water returns almost nothing.
Okay.
The sonar system takes all those returning echoes and mathematically reconstructs them into a top-down 2D video feed.
Wow. And that completely solves the turbidity problem.
Completely.
Because glacial flour doesn't block sound waves the way it blocks light. So pitch black, milky water, heavy silt, the sonar just slices right through it and gives you a glowing outline of every single fish moving up the river.
It is a phenomenal technological victory, truly. But in solving the sensory problem, they inadvertently created a massive computational problem.
Because now you have an avalanche of data.
An absolute deluge. I mean, think about it. A sonar camera running 24 hours a day, 7 days a week, over a 6-week salmon run.
That's got to be huge.
It generates terabytes of raw video. It is hundreds and hundreds of hours of high-resolution acoustic imaging.
Right.
And someone or some machine still has to actually watch all of that footage to count the fish.
Which brings us right back to our technician in the freezing tent. Up until this new MIT and Caltech paper, there was a standard state-of-the-art way to process this sonar video using AI. Let's break down what that incumbent pipeline looks like, because I really want to fully understand the baseline before we talk about the new invention.
Sure, yeah. The prevailing, highly accurate approach in the field right now relies on a 2-stage deep learning pipeline. It's known as a detector tracker model.
A detector tracker, okay.
The most widely deployed configuration uses an object detection model called YOLO 5-meter, and that's paired with a tracking algorithm known as SORT.
Okay, I've actually heard of YOLO. It stands for You Only Look Once, right?
That's right.
It's a hugely popular architecture in computer vision. But what does the V5 meter stand for, and how heavy is this thing computationally?
Well, the V5 is just the version number, and the M stands for medium. But medium in the world of deep neural networks is very relative.
I bet.
This specific YOLO model contains roughly 21.2 million parameters.
21.2 million parameters.
Okay, so for anyone listening who isn't a machine learning engineer, a parameter is essentially a tunable dial or like a weight inside the neural network.
Exactly.
The model uses those 21 million dials to process the pixels and make a decision about what it is looking at.
That is a perfect way to conceptualize it. Now, consider how a video actually works. Video is just a sequence of still images played in rapid succession, typically 30 to 60 frames per second.
Right.
The YOLO detector approaches the sonar video in the most computationally expensive way imaginable. It analyzes it frame by individual frame.
Oh, wow. Walk me through that. What is the YOLO model actually doing mathematically when it looks at frame number 1?
It takes the entire image and divides it into a grid. For every single cell in that grid, the 21.2 million parameters run a massive series of calculations to predict bounding boxes.
Bounding boxes?
Yeah, literally drawing a rectangle around any cluster of pixels it believes is a fish. It also calculates a confidence score for each box.
Then it moves to frame number 2, completely starts over, and runs those 21 million calculations all over again. Frame 3, repeat. Frame 4, repeat.
But wait, just drawing boxes doesn't give you a count.
No, it doesn't.
Because if I'm a salmon and it takes me 10 seconds to slowly swim across the camera's field of view at 30 frames per second, that YOLO model has drawn 300 boxes around me across 300 different frames.
Exactly.
If you just sum up the boxes, you would think 300 salmon went by.
Which is exactly why you need the second stage of the pipeline, the sort tracker.
Okay, the tracker.
SORT stands for Simple Online and Real-Time Tracking. The tracker's job is to act as the spatial memory for the system.
How does it do that?
It uses mathematical models, specifically things called Kalman filters, to predict where a box from frame 1 should theoretically be in frame 2.
Oh, I see.
It looks at all the boxes generated by YOLO and stitches them together into a continuous trajectory. It deduces, okay, the box in frame 50 is the exact same biological entity as the box in frame 51, just shifted slightly to the left.
So it connects the dots. It links hundreds of boxes into one single trajectory line, and then it just counts the lines.
Precisely.
It also figures out if that line is moving left to right or right to left, giving you the upstream versus downstream direction.
That's right. And in terms of pure accuracy, this two-stage detector tracker pipeline is phenomenal.
Like, how phenomenal?
Well, when evaluated on the Caltech Fish Counting dataset, which, remember, contains over 500,000 human-annotated frames from actual rivers in Alaska and Washington,
Yeah.
the error rate is incredibly low. On familiar rivers, what data scientists call in-distribution data, the heavyweight YOLO pipeline achieves a normalized mean absolute error of just 4.9%.
4.9%. Wow. That means it is roughly 95% perfectly accurate at replicating a trained human's count.
It's incredibly impressive.
So they did it. They built a machine that can watch sonar and count fish almost perfectly. Why on earth are these researchers spending their time inventing a new system if the current one already works that well?
Well, because the accuracy metric ignores the operational reality of the deployment environment.
The freezing tent.
Exactly. To run a 21.2 million parameter deep neural network, applying it to every single frame of a high-resolution video stream running at 30 frames per second, it requires an immense amount of compute.
Let me throw an analogy at this to see if I have the scale right. Trying to process that much data on a standard laptop CPU is like trying to pipe the entire volume of Niagara Falls through a standard garden hose.
That is a very accurate analogy.
The volume of data simply exceeds the physical bandwidth of the hardware.
Right. A standard consumer laptop on a gravel bar physically cannot process 30 frames per second through a 21 million parameter network.
It would just melt.
It will overheat, throttle its performance, and eventually choke. To run the YOLO pipeline in real time, you need dedicated, high-end graphics processing units, or GPUs.
Which you don't have in a tent.
And you need a stable, heavy power supply to run those GPUs, which a small portable generator absolutely cannot reliably provide.
Okay, and if you can't run it locally on the gravel bar, your only other option is to send the video to a place that does have the hardware.
Right.
You have to upload it to the cloud, to a server farm in Seattle or Silicon Valley.
But remember the environment. There is no fiber optic cable running to the Nujigac River. There is rarely even a cellular signal.
Yeah, you're out in the absolute middle of nowhere.
You cannot upload terabytes of video over a satellite connection.
Yeah.
The bandwidth costs would be astronomical, and the latency would be prohibitive. The authors of the preprint point this out explicitly.
What do they say?
They state that frame-by-frame deep network processing is, quote, currently unsuitable for deployment in locations with limited compute and connectivity.
But, okay, I want to push back on this a bit because I am trying to think like a pragmatist here.
Sure.
If the YOLO tracker is 95% accurate and the data is that important, why not just be patient?
How do you mean?
Like, let the sonar camera record the raw video onto a massive hard drive. At the end of the week or the end of the month, a float plane or a helicopter lands on the gravel bar. A technician swaps out the hard drive, flies it back to a laboratory in Anchorage that has the massive GPUs, and we process the perfect data then.
Ah.
Why is running the AI on the laptop in the tent the absolute prerequisite?
To understand that, we have to look at the daily logistics of fisheries management. You see, the managers of these rivers are not conducting a historical academic audit of what happened last month.
Right.
They are actively managing a live, dynamic biological event with immediate economic consequences.
Oh, because the commercial fishing fleets are waiting out in the ocean?
Exactly. At the mouth of the river, waiting for permission to cast their nets.
Oh.
The managers have strict, legally mandated escapement targets.
Okay.
Let's say the biological model dictates that 500,000 salmon must successfully make it up the river to spawn in order to sustain the population for future generations. The manager is watching the daily count. If by Tuesday the run is severely lagging behind the historical curve and only 50,000 fish have passed, the manager must issue an emergency executive order to close the commercial fishery downstream on Wednesday morning.
Because every fish caught in the ocean is a fish that won't make it to the spawning grounds.
Right. But if the manager waits 2 weeks for a float plane to retrieve a hard drive and a lab in Anchorage to process the YOLO data, they are flying blind.
Oh, wow. Yeah.
They might accidentally leave the commercial fishery open during a weak run, allowing the fleet to overfish and potentially collapse the population for the next decade.
That makes total sense.
Delayed data, no matter how perfectly accurate it is completely useless for active, in-season management. They need the count today.
Wow. Okay, so an AI model with a 4.9% error rate that requires a lab in Anchorage effectively has a 100% failure rate for the manager who needs to make a decision at 5:00 p.m. this afternoon.
That's exactly it.
A 0% error rate on delayed data is a total systemic failure.
Precisely. So the engineering paradigm fundamentally shifts here. The question is no longer, how do we build an AI that counts fish more accurately?
Right.
The question becomes, how do we build an AI that can count fish at all on a cheap laptop with a garden hose-sized processor?
And this brings us to the core innovation. This is the entire reason we are doing this deep dive.
Yes, it is.
The researchers from MIT and Caltech realized that if the laptop physically cannot process a video frame by frame, they had to ask a pretty radical question.
They did.
What if we stopped treating the sonar data like a moving video?
It is the most beautiful, counterintuitive leap in the entire paper.
Yeah.
They decided that if computing time is the bottleneck, they would simply take time, which we experience sequentially in a video, and squash it entirely into physical, two-dimensional space.
I am fascinated by this concept. Walk me through the exact physics of how you compress a moving video into a flat 2D picture. Introduce us to the Echogram.
Okay, let's visualize the sonar camera sitting in the water again.
Okay, visualizing it.
It pulses sound across the river, and it captures one single frame of video. That frame represents a top-down view of the river at 1 exact millisecond.
It's a 2D matrix of pixels. The y-axis of that frame is the distance away from the camera, and the x-axis is the width of the sonar beam.
Right. Now imagine taking that entire 2D snapshot and mathematically crushing it down into a single, thin, vertical column of pixels.
Just squishing it.
Exactly. We throw away the entire horizontal width of the image. We only keep the y-axis, which is the radial distance from the camera.
Okay.
The top of this vertical strip represents the water right in front of the lens. The bottom of the strip represents the water far out across the river.
Wait, if you are squashing the entire width of the frame into a single vertical line, how do you decide what color or brightness a pixel on that line should be? You are combining dozens of pixels into one.
You take the maximum intensity.
Okay, how does that work?
For any given distance away from the camera, you look horizontally across the entire original sonar fan. If there is a bright acoustic reflection anywhere at that specific distance, meaning a fish is present, you make that pixel on the vertical strip bright.
Ah, I see.
If there is nothing but empty water across that entire distance, the pixel on the vertical strip is dark. You are collapsing the 2D space into a 1D summary of, is there a fish at this distance, yes or no?
Okay, so one frame of video has now become one single vertical line of pixels.
Now, take the next frame of video, a 1/30th of a second later, you crush it into a vertical strip, and you place it right next to the first one.
Got it.
Then you take the third frame, crush it, and place it next to the second. You do this continuously, stacking these vertical strips side by side, moving from left to right.
And suddenly, as you stack these lines, a new 2D rectangle begins to form.
Yes, you have created an echogram. It is a completely new representation of the data. The y-axis is still the physical distance from the camera, but the x-axis is no longer spatial width. The x-axis is now time. Reading the image from left to right is literally reading forward in time.
The researchers use some fantastic analogies in the dossier to make this concrete because it's a bit of a mind bender.
It really is.
If you are trying to picture what an echogram actually looks like, imagine a photographer taking a long exposure photograph of a busy highway at night.
That's a great one.
If you take a standard fast shutter photo, you see the distinct shapes of individual cars. That's like a single video frame. But if you leave the camera shutter open for 30 seconds, the individual cars disappear.
Right.
They turn into these continuous glowing ribbons of light stretching down the asphalt.
That is a brilliant way to visualize it.
Mm-hmm.
In the echogram, as a salmon swims through the sonar beam over a period of, say, 5 seconds, it does not appear as a fish-shaped blob.
Right, because it's squashed.
Because its distance from the camera is constantly changing over time, it traces a diagonal streak or a glowing smudge across the image. The slope of that streak, the angle of it, encodes how fast the fish was moving and exactly when it entered and exited the beam.
The other analogy the authors use, which I think is incredibly apt for what the AI is about to do, is calling the echogram a barcode of the run.
Yes, the barcode.
If you look at a product barcode at the grocery store, it's just a dense, chaotic pattern of vertical lines. An echogram looks like a glowing, messy barcode.
It really does.
And just like a laser scanner can sweep across a barcode in one single pass to read the data, a computer vision model can look at this flat echogram and read the dense pattern of smudges to understand the flow of traffic.
It is a profound shift in data architecture. You have taken an event that you previously had to watch unfold over hundreds of frames, and you have frozen it into a static space that you can see all at once.
But hold on, let's play devil's advocate here, because in squashing that data, we've created a massive logical problem.
Oh, absolutely.
If we take the whole 2D frame and flatten it into a single vertical column of maximum intensity, we have deliberately thrown away the horizontal axis.
Right.
We threw away the lateral side-to-side movement across the camera view.
We did. We collapsed the entire width of the beam into a single point.
But if we throw away the lateral movement, how do we know which direction the fish is swimming?
That's the catch.
Like a fish swimming upstream to spawn and a dead log floating downstream with the current might both create a diagonal streak on the echogram because their distance from the camera is changing over time.
Correct.
If we don't know if they entered from the left side of the screen or the right side of the screen, we can't subtract the downstream debris from the upstream count. We just ruin the data for the managers.
This was the exact bottleneck the engineering team had to solve, and their solution is just incredibly elegant.
Okay, what did they do?
They realized that a standard image isn't just one flat layer of pixels. A digital image is made of channels.
Like an RGB image on your phone has a red channel, a green channel, and a blue channel layered on top of each other.
Exactly. So instead of creating a standard single-channel grayscale image, the researchers created a two-channel echogram. They built a dual-layer encoding system.
Okay, let's break down those layers.
The first channel, the first layer, is exactly what we just discussed. It stores the maximum intensity. This is the brightness layer.
Okay.
It tells the computer, yes, there is a strong acoustic echo at this specific distance, at this specific time. This layer generates the physical shape of the streaks.
Is a fish there layer? What is the second channel doing?
The second channel acts as the spatial memory. For every bright pixel in the first layer, the second layer records where that echo originated horizontally before it was squashed.
Oh, wow.
It looks at the original wide sonar beam, identifies which specific acoustic slice returned the echo, and normalizes that horizontal position into a mathematical value between 0 and 1.
I want to pause on that normalization step because that is a classic machine learning technique. Why normalize it between 0 and 1 instead of just feeding the AI the raw pixel coordinates like pixel 450?
Well, neural networks are highly sensitive to the scale of the numbers you feed into them.
Okay.
If you feed a network very large, raw numbers like pixel coordinates in thousands, the mathematical gradients during training can become unstable.
Unstable how?
They can explode or vanish entirely, meaning the network simply fails to learn. By normalizing the data, squishing it so that the far left edge of the sonar beam is represented by a 0.0, the middle is 0.5, and the far right edge is 1.0, you keep the math tightly bounded and easily digestible for the neural weights.
That makes perfect sense. So channel 1 has the bright streak, and channel 2 has a gradient of numbers from 0 to 1 layered exactly over that streak.
Yes. And by combining those two layers, you preserve just enough of the original side-to-side path to determine direction.
How exactly?
A downstream object might have values in the second channel that start near point 1 and progress toward point 9. An upstream fish will show values progressing from point 9 down to point 1. The directionality is mathematically preserved without needing to keep the full, heavy video frames.
That is just brilliant. They extracted the bare minimum biological telemetry required and discarded the rest.
Yes, they did.
And let's talk about the raw computational math of what this compression achieves, because this is where the garden hose laptop finally gets a reprieve.
The spatial savings are staggering. The researchers sliced the continuous echogram into discrete blocks. The input fed to the model is just 200 pixels tall by 800 pixels wide.
Wait, 200 by 800?
Yes. The y-axis, representing the distance across the river, is compressed to 200 pixels. The x-axis, representing time, captures a 200-frame window of original video stretched across 800 pixels.
Let me do the math on that. A typical high-resolution sonar frame might be millions of pixels. 200 frames of that is hundreds of millions of pixels of data that YOLO would have to process. The echogram compresses all of that temporal and spatial data down into a single image that is 200 by 800 pixels. That's 160,000 pixels. Millions of pixels of moving imagery are reduced to a single, manageable 200-frame window.
You have turned a massive, heavy video file into the computational equivalent of a tiny, low-resolution JPEG.
We took the movie and we made a barcode.
Exactly.
But here is the next logical hurdle. Now that we have this compact, glowing barcode, we still need a machine to read it.
Right.
You can't use the YOLO object detector anymore, right?
Absolutely not.
YOLO looks for distinct shapes to draw boxes around. There are no fish shapes in an echogram. There are just diagonal smudges.
Exactly. You cannot use a bounding box tracker on an echogram because the biological objects do not visually exist in a traditional sense anymore.
Right.
The engineering team successfully transformed a complex temporal tracking problem into a much simpler classic image recognition problem. And because the problem is simpler, you don't need a 21 million parameter behemoth to solve it.
Enter the new hero of the story, the ResNet 18 model.
Yes. ResNet stands for residual network, and the 18 refers to the fact that it is 18 layers deep.
Okay.
It is a highly respected, heavily utilized, lightweight neural network architecture. Compared to YOLO's 21.2 million parameters, ResNet 18 operates with roughly 11.7 million parameters. It is nearly half the size.
And what blows my mind is that ResNet 18 wasn't even built to look at sonar data or fish. It's a general-purpose image scanner.
It is entirely general purpose. In fact, standard ResNet models are typically pre-trained on a dataset called ImageNet.
I've heard of that.
Yeah, ImageNet is a legendary massive database containing millions of everyday photographs: dogs, cats, coffee mugs, cars.
So wait, how does a neural network trained to recognize a coffee mug help us count salmon smudges on an acoustic echogram?
It's all about how convolutional neural networks, or CNNs, learn to see. When you train a model on ImageNet, the earliest layers of the network aren't learning what a dog is.
What are they learning?
They are learning fundamental visual physics. They learn how to detect a sharp edge. They learn how to recognize a gradient, a shadow, or a specific texture. They build a foundational mathematical vocabulary of computer vision.
So they learn the alphabet of vision even if they are eventually going to read a different language?
Precisely. The researchers take this pre-trained ResNet 18 model, which already possesses a deep intuition for processing textures and edges, and they fine-tune it.
On the fish data.
Right. They expose it to thousands of examples from the massive Caltech Fish Counting dataset, over 500K frames, 8,254 fish, from 7 cameras across the Kenai, Nushagak, and Elwha rivers.
That's a lot of data.
It is. They feed it an echogram image, and they tell it, this specific pattern of smudges equals exactly 15 upstream fish. They do this over and over again, altering the internal weights of the network until the model learns to correlate the dense overlapping textures of the echogram with a specific numerical count.
And this leads to a detail that completely rewrites how I thought AI counting worked. Like, here's where it gets really interesting for the listener. As the ResNet 18 model reads the echogram, it never draws a box.
Never.
It never isolates a single fish. It doesn't track anything.
It doesn't even possess the concept of an individual fish.
Right. If you somehow ask the model, hey, point to the third fish that swam by, it couldn't do it.
Because it is performing a mathematical regression, not object detection, It is reading the holistic texture of the image.
Okay.
The model digests the entire 200 by 800 pixel window at once. It looks at the density of the bright pixels, it looks at the slope of the streaks generated by the two-channel encoding, and it directly outputs two continuous numbers. Account for fish going left and account for fish going right.
It reads the barcode without ever identifying a single item on the shelf. It just looks at the overall density of the blur and says, the math of that blur equals 14 upstream fish.
And this is where the computational victory is finally realized on the gravel bar. Think back to the YOLO pipeline. It was executing 21 million parameters, drawing boxes, and updating Kalman filters 30 to 60 times every single second.
The garden hose bursting.
Exactly.
Yeah.
Because the Echogram compresses 200 frames of time into one single static image. The ResNet 18 model only has to execute its calculation once for that entire block of time.
It just takes one glance.
One single forward pass through an 11.7 million parameter network every 200 frames. The computational load drops off an absolute cliff.
Wow.
You have completely replaced the paradigm of look intensely, process heavily 60 times a second with a new paradigm of glance casually once every few seconds at mathematical summary.
And because it is only glancing, and because the model is half the size, the consumer laptop on the folding table doesn't overheat. It doesn't throttle. It easily digests the data in real time, powered by a basic generator, completely severed from the cloud.
It is a triumph of data representation. But as with all engineering, we have to address the reality of physics. You do not aggressively compress space and time without paying a tax.
Right. There is no free lunch in computer science. If we are squashing the data this heavily, we are losing fidelity. We have to look at the cold, hard numbers because the authors of the preprint are brutally honest about the trade-off they made.
They are completely transparent, which is the hallmark of good science. We have to look at the normalized mean absolute error, the NMAE, to see exactly what this compression costs in terms of raw accuracy.
Let's lay out the stats straight from the February 2025 dossier. As a reminder, the heavyweight YOLO pipeline, the one that requires the lap in Anchorage, achieved a 4.9% error rate on familiar in-distribution rivers.
Right.
When tested on brand new rivers it had never seen before out of distribution data, it degraded slightly to an 11.8% error rate.
Now compare that to the performance of the Echogram with the lightweight ResNet 18 reader.
On in-distribution data, specifically looking at the Kenai lift bank camera feeds, the ResNet 18 error rate jumps to 23%.
Yeah.
And when tested on out-of-distribution data, like the Kenai right bank, the error climbs to 30.7%.
That is a massive drop in accuracy. We were talking about an error rate that is essentially 4 to 6 times higher than the state-of-the-art detector.
So what does this all mean for the decision makers? Like, I have to play the role of the skeptical fisheries manager here.
Okay, go ahead.
I am legally responsible for the biological survival of a keystone species and the economic livelihood of hundreds of commercial fishing families. A 30% error sounds utterly terrifying.
It does.
If my true count is 100,000 salmon, but my laptop tells me only 70,000 went by, I might mistakenly keep the fishery closed, bankrupting the fleet for no reason. Or worse, I might think 130,000 went by, open the fishery, and allow the fleet to decimate a fragile run. How can I justify using this?
That is the ultimate operational dilemma, and it is a subject of intense, active debate among statisticians and biologists.
So how do they justify it?
To understand if a 23% error is acceptable, we have to dig deep into a critical statistical concept: the profound difference between noisy data and biased data.
Okay, let's strip this down. What does it mean if the 23% error is biased?
If the error is biased, it means the model is systematically making the exact same mistake in the exact same direction every single time.
Give me an example.
For example, let's say the Echogram compression blurs the acoustic signature of smaller salmon so much that the ResNet model simply cannot perceive them. If that happens, the model will systematically undercount the run by 23% every single day.
It's like using a bathroom scale that is broken and always reads exactly 5 pounds too light.
Exactly. If the data is biased, a 23% error is incredibly dangerous. Because if you are undercounting by 23% on Monday, and 23% on Tuesday, and 23% on Wednesday, that error compounds.
Oh, yeah.
By the end of the season, your cumulative total is off by millions of fish, leading to catastrophic management decisions.
That's bias.
Yeah.
What happens if the 23% error is noisy?
If the error is noisy, it means the mistakes are somewhat random and normally distributed. It means the model is struggling with the exact count, but not in a systematic way.
Like it's just guessing a little high or a little low.
Right. Maybe on Tuesday at 9:00 a.m., a dense cluster of fish swims by, and the model overcounts by 20%. But on Tuesday at 2:00 p.m., a similar cluster swims by, and due to random variations in the echogram texture, it undercounts by 15%. On Wednesday, it overcounts by 5%.
It's scattering its guesses around the true number.
Yes. And if you are familiar with statistics, you know what happens to a random normal distribution of noisy errors over a massive sample size.
They average out.
Exactly. Over a long enough timeline, like a full 6-week salmon season involving millions of individual fish, those noisy overcounts and undercounts naturally begin to cancel each other out. The peaks fill in the valleys, and the cumulative average mathematically drifts closer and closer to the true objective mean.
It's like political polling. Any single poll might be wildly wrong due to noise, but if you aggregate 100 noisy polls, the average is usually incredibly accurate.
That's a great analogy. And for a fisheries manager, consistent noisy data is often perfectly usable. Managers frequently care far more about the trend than the absolute integer count.
What do you mean?
They want to know, is the run accelerating today compared to yesterday? Has it peaked? A model with 23% noisy error can still plot a highly accurate relative trend line that perfectly maps the shape of the biological event.
However, we have to be completely intellectually honest here. The preprint doesn't definitively prove whether this new echogram error is perfectly noisy or if there is an underlying systematic bias, right?
That is a crucial caveat. The dossier makes it clear that this is still an open question in the research. The authors have proposed a novel representation, but they haven't run the multi-year comparative biological audits required to prove the statistical distribution of the errors.
So we can't be certain yet.
No, we cannot blindly assume the 23% error will perfectly come out in the wash until further rigorous field testing confirms it.
But even with that mathematical uncertainty hanging in the air, we are forced right back to the brutal logic of the gravel bar.
We always come back to the gravel bar.
The final verdict on this accuracy trade-off is this. A 23% error that actually runs on the laptop in the tent, giving the manager a trend line today, infinitely beats a 5% error that requires a lab and takes 2 weeks to process.
It is the classic military adage. It is the difference between having a rough, hand-drawn map of a minefield right now while you are standing in it versus having a perfect millimeter-accurate satellite map mailed to you a week after you already tried to walk through.
Yeah, exactly. The rough map is exponentially more valuable.
Precisely.
There is also a numerical quirk in the text I want to highlight because I think it speaks to how AI actually develops.
Oh, what's that?
The dossier mentions that an earlier proof of concept landed around 19.3%, so the method has room to improve. Wait, if the old proof of concept had a 19.3% error and the new, fully realized system has a 23% error, didn't they actually make it worse?
It looks like a regression on paper, but it is actually a hallmark of AI maturation. When researchers build an initial proof of concept, they often test it on a highly curated, highly sanitized, and very small subset of data. It's a controlled laboratory environment, and the model naturally performs exceptionally well.
It memorizes the test.
Precisely. But when you expand that concept into a robust system, and you force it to generalize across the massive chaotic variations of the full Caltech dataset, incorporating different rivers, different camera angles, different water flows, and different lighting conditions, the error rate naturally rises.
Because it's encountering edge cases it hasn't seen before.
Exactly. It's the penalty for moving from the laboratory into the messy real world. The jump from 19.3% to 23% proves that this is a rapidly developing technology, a young representation of data, not a stagnant finished product.
I see.
Because the echogram is such a novel concept, there is immense room for the neural architecture to improve as researchers gather more diverse training data and tweak the model layers. So we shouldn't see it as a finished replacement, but rather a developing technology.
Okay, so we've established that we sacrifice some mathematical precision in the raw count to gain speed. But squashing 3D time into a flat 2D image means we also discard physical reality.
Yes, we do.
When we collapse a whole video frame down to just the single brightest acoustic echo on a vertical strip, what else gets left on the cutting room floor? Like, what is the biological toll of this compression?
The toll is paid in fine detail, and in biological sciences, detail is often paramount. Because the echogram intentionally reduces the complex acoustic return of a fish into a simplified streak of maximum intensity, we completely obliterate the morphology of the animal.
The morphology, you mean its shape?
We lose its physical shape, its volume, and its subtle movements.
You mean we can't tell how long the fish is?
Exactly. And length is a critical metric because it is the primary proxy for species identification.
Oh, right.
For many management agencies, counting isn't just about total biomass. It is about knowing the exact composition of the run. They need age, sex, and length data, often called ASL data.
ASL data, okay.
They need to know exactly how many large Chinook salmon went by versus how many smaller sockeye salmon.
Because the Chinook might be endangered and require strict protection, while the sockeye are abundant enough for commercial harvest.
Right. A traditional YOLO tracker, because it is analyzing the full, high-resolution video frame, can potentially measure the pixel length of the bounding box and make an educated guess about the species.
But the Echogram can't.
The Echogram cannot do that. A large Chinook and a smaller sockeye might both just look like a glowing 0.8 intensity smudge.
What happens when the biological reality gets messy? What happens when two fish swim right next to each other?
That introduces a severe limitation known as occlusion.
Occlusion.
Yes. If two salmon pass through the sonar beam at the exact same distance from the camera, at the exact same time, their maximum intensity echoes will mathematically merge on the vertical strip.
Oh, I see.
On the echogram, they will manifest as a single, slightly brighter streak. The ResNet model, reading that texture, might only count one fish.
Whereas the YOLO video tracker, looking at the full visual plane, would clearly see two distinct bodies overlapping and track them separately.
Yes. The echogram intentionally sacrifices deep, nuanced biological insights for raw, immediate bulk counts.
It trades a scalpel for a sledgehammer. Because sometimes the manager doesn't need to know the cellular makeup of the rock. They just need to know roughly how heavy the rock is today so they can make a binary yes or no decision on the fishery.
That is the perfect characterization. It is a highly specialized tool designed for a very specific operational constraint. It is not a universal replacement for all scientific observation.
Which perfectly sets up the final and, to my mind, the most impactful aspect of this entire preprint.
Okay, where are we going with this?
Because despite the biological losses and despite the 23% error rate, the invention of the echogram model does something far more important than just counting fish initially. It fundamentally changes who gets to do the counting.
Oh, absolutely. This is where the engineering breakthroughs cascade into sociology, economics, and field dynamics. We have to examine how computational architecture either centralizes or decentralizes human power.
Let's break that down. How does the traditional state-of-the-art AI pipeline concentrate power?
Think about the infrastructure required to run that 21.2 million parameter YOLO model. You need expensive, high-end GPUs. You need enterprise-level cloud computing accounts with Amazon or Google.
Which costs money.
You need high-speed internet infrastructure. And critically, you need a salaried team of software engineers and data scientists to maintain that complex pipeline.
Which means only massive, well-funded organizations can play the game.
Exactly. That hardware and financial requirement naturally concentrates the power of data analysis in the hands of large, centralized state or federal agencies, major university laboratories, or massive corporate data centers.
Leaving the people on the ground out of the loop.
Right. The people actually on the riverbank, the local technicians sitting in the rain, are reduced to mere data collectors. They gather the raw sonar files, but they have to hand them over to the centralized authority to extract the meaning. The field station is entirely dependent on the lab in the city.
But the echogram flips that entire dynamic on its head. This is the edge computing revolution applied to conservation.
Yes.
Moving the heavy computational lifting to the edge, meaning processing the data locally on the hardware that is right there where the data is being generated, shifts the control back to the riverbanks.
It radically empowers the local field station workers. They no longer have to wait 2 weeks for a lab in Anchorage to tell them what they saw with their own eyes.
They can do it themselves.
They can run the lightweight ResNet 18 model on their own battery-powered laptop and get the count themselves that same evening by the glow of a camp lantern.
The democratization of this technology is profound. Because it relies on cheap, off-the-shelf consumer laptops and open-source models, it completely shatters the financial barrier to entry.
It really does.
This means that a small tribal government or an independent localized conservation nonprofit or a small community watershed group can now participate in high-level AI monitoring.
Yes. If a local tribal agency can scrape together the initial funding to purchase the sonar camera, they no longer have to worry about paying massive, ongoing subscription fees for cloud computing.
Or hiring a team of machine learning engineers.
Exactly. They can process their own data entirely on-site.
They maintain total sovereignty over their own environmental metrics. They aren't locked out of the AI conservation revolution just because they don't have a fiber optic cable running to their local gravel bar.
By making the AI smaller, simpler, and slightly less accurate, the engineers have allowed it to exist in thousands of remote places it could never possibly exist before.
So let me ask the ultimate question for the field of computer vision for conservation. Is this the future? Will the heavy, highly accurate YOLO pipelines just disappear now that we have this elegant Echogram barcode?
I would strongly caution against viewing this as a zero-sum game or a total replacement.
Okay, why not?
The Echogram is an elegant demonstration of a new capability. It is a vital new tool added to the toolbox. But the field will likely bifurcate.
Meaning split in two.
Right. If you are managing a counting station that does have grid power and does have a high-speed internet connection, perhaps a dam on a major river near a city, you will absolutely continue to deploy the heavy, highly accurate detector trackers. You want that 4.9% error rate when the infrastructure allows you to afford it.
Use the Ferrari when you have a paved track.
Exactly. But for the vast majority of the world's waterways, which are remote, hostile, and utterly lacking in compute infrastructure, the Echogram provides a critical lifeline. It ensures that perfect data doesn't become the enemy of necessary data.
It is just a brilliant piece of problem solving. Let's summarize the journey we've been on today because we covered a lot of ground.
We certainly did.
We started with a seemingly impossible physical bottleneck, trying to process a relentless flood of high-resolution sonar video inside a freezing Alaskan tent with no internet and no real computing power.
Right, the gravel bar.
We saw how the traditional AI, the heavy 21 million parameter YOLO tracker, could achieve a near-perfect 4.9% error rate, but completely failed the basic operational test of being usable on a cheap laptop.
And the solution to that bottleneck wasn't brute force. The engineers didn't try to build a better battery or invent a faster laptop CPU or launch a new satellite for better internet.
Yeah, what they
The
did.
solution was to reimagine the fundamental physics of the data itself.
They took 200 frames of moving video representing the flow of time, and they mathematically squashed it down into a single, flat, two-channel, 200 by 800 pixel image.
The Echogram.
They created the Echogram, a long-exposure barcode of the river that perfectly preserved the direction of the fish while throwing away millions of unneeded pixels. And by doing that, they allowed a lightweight, 11.7 million parameter image scanner, an off-the-shelf ResNet 18 model designed to recognize cats and chairs to read the complex flow of the salmon run in a single effortless glance.
They willingly traded a 4.9% error rate that requires a supercomputer for a 23% error rate that runs on a folding table in the mud.
Yeah.
They deliberately traded deep biological detail, like the exact length of a fish, for raw, immediate, actionable speed.
And in doing so, they gave those remote technicians the power to count salmon in real time, completely off the grid, shifting the power of conservation data back to the people who are actually standing on the riverbanks.
It's empowering.
If we step back and connect this hyper-specific engineering feat to the bigger picture, to our everyday lives, it really forces you to reevaluate how we approach problem solving.
It does. In this current era of massive information overload, we often default to assuming we need the biggest, most complex, most power-hungry AI models to solve our issues.
Right. We think bigger is always better.
We want the absolute heaviest computational hammer available. But this research proves that sometimes the most elegant, effective solution isn't to build a bigger machine to process the data. Sometimes the absolute genius lies simply in changing how you represent the data so a smaller machine can easily understand it.
It is a profound lesson in efficiency. So I want to leave you, the listener, with a final thought to mull over as you go about your day.
That's a good one.
If these MIT and Caltech researchers could solve an impossible ecosystem-level computing bottleneck simply by re-encoding time into physical space, literally turning a heavy movie into a lightweight barcode, where else in your own life or your own work are you trying to painstakingly analyze every single frame of a problem? Where are you exhausting yourself trying to track every tiny moving detail when you should really just be stepping back, squashing it all down, and looking at the holistic barcode of the whole picture?